Hello everyone, I am Seshavidya, working in R.M.K College of Engineering and Technology as Associate Professor in the Department of ECE. So today we are going to discuss digital electronics in that first unit, digital fundamentals. So in the digital fundamentals, first we are going to discuss number system. So before going into this number system, first we should know what is the necessity of that number system. So as we know that the digital circuit, it operates with binary numbers. That is only in two states. That is output of the circuit is either low or high. So low means we can just represent it as 0 and high means we can just represent it as 1. And in this we are going to discuss the number system and then how to convert from one number to another and then ones and twos complement. So when considering this number system, there are four types of number systems: binary, decimal, octal and hexadecimal. So even though this binary, octal and hexadecimal is there, this decimal number is very important. It is commonly used in many applications. So this is binary. So a binary is nothing but base 2, that is weights in power of 2. So binary digits, as I told, and it has only 2 bits, 1 and 0. And decimal is nothing but which can be represented as base 10, that is weights in power of 10. So decimal digits starts from 0 and to 9, that is 0 to 9. And then octal, which can be represented as base 8 and which can be represented also in terms of weights in powers of 8. So this octal digits which starts from 0 to 7. And next one is hexadecimal. So this is base 16, that is weights in powers of 16. So hexadecimal digits from 0 to 9. Next to 9, it starts from A to F. So this is about number system. As I told you, so this is a graphical representation of number system. Binary, base 2, so it uses zeros and ones. Octal, it's base 8 and it uses the digits from 0 to 7. Decimal means base 10, which uses the digits from 0 to 9. So last one is hexadecimal, which is nothing but base 16. It uses the digits from 0 to 9 and alphabets from A to F. This binary number system, that is how to give that the powers of 2. So we can just represent that weights in terms of power of 2. So as I told you, it has only two digits, 0 and 1, and we can just represent that base in terms of 2. Why? Because it's in binary. And say for example, this is a binary bit 1 0 1 1. So we can just represent in terms of powers of 2. That is, we can write it as 1 0 1 1. And we can just give that weights that starts from, yeah, this one is nothing but MSB bit and this is nothing but LSB bit. Okay, so from this LSB bit you can start writing that powers of 2. So this is 2 power 0, 1 into 2 power 1, 0 into 2 power 2, 1 into 2 power 3. Okay, so we are starting from LSB bit. So 1 into 2 power 0, again 1 into 2 power 1, 0 into 2 power 2 and 1 into 2 power 3. So likewise we can just represent weights in terms of power of 2. This is binary number system. Next, number system. So as I told you, digits which will have from 0 to 9. So totally 10, so that we can just represent the decimal number as 10. And say for example 7, 2, 4, 5, we are considering one decimal number. Suppose if you want to represent in terms of weights, then we can just write it in terms of, that is again from LSB bit to MSB bit. So 5 into 10 power 0, 4 into 10 power 1, 2 into 10 power 2, 7 into 10 power 3. So likewise we can just represent weights in terms of decimal number system. So next, octal number system. So octal number system which will have the digits from 0 to 7. So we can just write the base as 8. So 8 represents octal number system. So say for example, this is one octal number 4637 and we can just represent that weights in terms of powers of 8. So 7 into 8 power 0, 3 into 8 power 1, 6 into 8 power 2 and 4 into 8 power 3. So always we have to represent, that is we have to start writing that weights from LSB bit to MSB bit. So next comes number system. So which will have the digits, that is from 0 to 9 and then alphabets from A to F. So base we can just represent as 16. So 16 means hexadecimal number system. So again, for example, I am considering that one hexadecimal number 2B6A. So which is the LSB bit? So A is the LSB bit. So we can start writing that powers of, that is in terms of power of 16. So A into 16 power 0, 6 into 16 power 1, B into 16 power 2, 2 into 16 power 3. So likewise, you can just represent the hexadecimal weight system. This table which gives the decimal number conversion table. So for the first column which represents decimal number from 0 to 15. The second column which represents binary number. So 1, so it is represented as 1, 2 means 10, 3 means 11, 4 means 100, 5 means 101, 6 means 110, and 7 means 111. So likewise we can write it up to 15. So this is, for example, I am just giving the decimal number conversion table from number 1 to 15. Similar way, the same decimal number that can be represented in hexadecimal also. So in hexadecimal number, as I told you, which will consist of the digits from, here it is 1, 1 to 9, and then alphabets from A to F. So here, for example, decimal number 10 means in hexadecimal it is A. So either you can just use capital letters or small letters. In decimal number, if it is 11, but in hexadecimal, which will represent as B. In hexadecimal 12, that is a decimal number is 12. In hexadecimal, we can just represent as C. So likewise, we can just represent up to 15. Similar way, octal number system. So which starts from 1 to 7. Next to 7, we can just count it as 10, 11, 12, 13, 14 and so on. So this is the decimal conversion table for the number from 1 to 15. So next one is conversion among bases. So as I told you, we have just discussed base 2, base 10, base 8, base 16. So based upon the binary, decimal, octal and hexadecimal. Now we can able to convert this numbers from one to another. So which represents decimal to octal, octal to decimal. Similar way, binary to decimal, decimal to binary. So likewise, any number that can be converted into the other form. So first we'll just consider binary to octal. Suppose if you want to convert any binary number to octal number, then you have to consider two steps. That is, first we have to, for the given binary number, that has to be grouped into 3. That is, 3 binary numbers as a group, we have to starting from the least significant symbol. That is, from the least significant symbol, we can just group that binary number into 3, 3. And then we can just write that equivalent octal digit for each group. So I'll tell you one example here. So say for example, so this is a given binary. So why it is binary? Why? Because base is 2. So we know that if base is 2, it is binary. And what is the conversion? It is given that convert 1, 0, 0 and then all 5 ones with base 2 to base 8, which means convert binary to octal. Base 8 means we know that it's an octal number. So the question is, we have to convert this binary number into equivalent octal number. So as I told you, what's the first step? So from the least significant bit, that is, which is the least significant bit? So this one is the least significant bit and this is nothing but most significant bit. So always we have to start from the least significant bit in such a way that we have to group 3 bits as a group. So this 3 as a group and this 3 as a group, and finally only 2 bits will be there, so that in the left hand side we can just add one more 0. Okay, so say for example, so I'm just splitting this 3 as a group, 1, 1, 0 as a group, and remaining is, here it is 0, 1 is there, only 2 digits are there, so that we can just add the one more 0 at the leftmost. Okay, now we can just write that equivalent. So triple 1, we know that triple 1 is nothing but 7, 0, 1, 1 is nothing but 3, 0, 1, 0 is nothing but 2. So that for the given number, that is for the given binary, the equivalent octal number is 2, 3, 7 with base 8. Okay, as I told you, the number of bit is not evenly divisible by 3 then add 0 at the most significant bit. So as we added here, so likewise, if it is not evenly divisible by 3, then we can just add 0 at the most significant end. Okay. So next one is octal to binary. So okay, so for each of the octal digit, we can just write the 3-bit binary equivalent. So that is the conversion. Again, for example, I'm just considering 3768. That is convert 376 with base 8, which means what? Octal. Convert that octal into binary. So in just reverse way you have to do. So what you have to do is for each that is an octal number, we can just write the 3-bit binary equivalent. So what is for 6? 6 is nothing but 110. 7 we can just represent it as 111. And 3 is nothing but 011. That is what you are writing. Just we are writing that the 3-bit binary equivalent for the given number. Okay, and given number is it's an octal. Why? Because base is 8. So now we can just write together 0, 1, 1 and then 111 and then 110 with the base. That's all. So likewise, we can just convert octal into binary. So what you have to do is here we have to use, please remember, we have to use 3 bits to represent. So each octal number that can be represented by 3 bits, equivalent 3 bits. Next one, binary to hexadecimal. So in the previous case, we have just for the given binary, we have grouped into 3, 3. But here since it is binary to hexadecimal, so we have to group into 4. And again, where we have to start? We have to start from the LSB bit. So say for example, this is a given binary number. Why it is binary? Why? Because the base is 2. So what's the conversion is? 2, the base 16, which means conversion is from binary to hexadecimal. So for the given binary, that is starting from the LSB bit, we can just group 4, 4. So 1, 0, 1, 0. So this 4 bits as a group and then this 4 bits 1, 0, 1, 1 as a group, and remaining how many bits are there? Only 2 bits are there. So how many bits we require? 4. So we can just add 2 zeros here. That is at the most significant end. So likewise. So I'm just grouping starting from the LSB bit and this 4 as a group, again this 4 as a group, and finally only 2 bits are there with this, which is understood that there are 2 zeros here. So anyway, we can write that equivalent. So 1010 actually in terms of decimal, which is equivalent to 10. But here we are going to write the hexadecimal equivalent. So 1010 is nothing but which is equivalent to A. And then 1011 is which is equivalent to, in terms of decimal it is 11. But in terms of hexadecimal it is B. So we can write it as B. And then it means that 0010, which is nothing but what? Which is the equivalent of 2. So finally we can write it as 2BA with the base 16. So for the given binary, equivalent hexadecimal number is 2BA with base 16. Okay, so as I told you, the number of bits is not evenly divisible by 4, then add zeros at the most significant end. As I told you, here we can just add 2 more zeros. So which is equivalent to 2. So likewise, we can just convert binary to hexadecimal. The next one is hexadecimal to binary. So just reverse process. The given hexadecimal, we can just write that 4-bit binary equivalent. So that's nothing but conversion from hexadecimal to binary. Say for example, I'm considering this example 3, 5, V1 with base 16, 2, base 2, which means what? Conversion from hexadecimal to binary. So straight away we can just write that 4-bit equivalent for the given hexadecimal. So likewise, 1 means 0001, B means 1011, 5 means 0101, 3 means what is that 4-bit equivalent? 0011. So for the given hexadecimal number, we can just write the 4-bit binary equivalent. Now we can just write together likewise 0011, 0101, 1011, 0001 with base 2. So for the given hexadecimal, this is the equivalent binary number. So as I told you, for every hexadecimal number, we can just write the 4-bit equivalent. In case of octal, we have to write it as 3-bit binary equivalent. But if it is hexadecimal, then we have to write the 4-bit binary equivalent. This is the difference between octal and hexadecimal. So far we discussed is binary to octal, octal to binary, and similar way binary to hexadecimal, hexadecimal to binary. So now we are going to convert this octal number to hexadecimal. So conversion is from octal to hexadecimal. So this octal to hexadecimal, which needs two steps. One is converting octal number to its binary, and then binary number to its equivalent hexadecimal equivalent. Say for example, it has 2 steps. So consider this example, convert 736.35 with the base 8 to base 16. So which means convert the base, that is octal number, to equivalent hexadecimal. So as I told you, what is the first step is, for the given octal number, first we have to write the equivalent binary. So we know that how to convert octal to binary. So for the given octal number, we can just write the 3-bit binary equivalent, and then finally by grouping that binary number as each 4, and then we can write the hexadecimal number. So I'll tell you how to write this one. So 736.35. So this is the given octal number. So for the given octal number, we are going to write the binary equivalent. So since it is octal to binary, so we have to write the 3-bit equivalent. So 6 means 110, 3 means 011, 7 means 111. And similar way, 3 is equivalent to 011 and 5 is nothing but 101. So we have converted the given octal number into equivalent binary. Now this binary that can be converted into hexadecimal. Now we know how to convert the given binary into hexadecimal equivalent. That is starting from the LSB bit by grouping each 4 bit as a group, isn't it? So what I'm going to do is 0, 1, 1, 1. So this 4 as a group, and then 1, 0, 1, 1 as a group, and finally there will be only 1 bit is there. So we can just write that. So remaining 3 bits are pending here. So we can just write the 3 bits as 0. So we can just add 3 zeros at the most significant end. Similar way, here also 0, 1, 1 and this one. So all this 4 bits as a group, and remaining only 2 bits are there. So that we can just add 2 more zeros at the least significant end. Okay. Now we can just write the equivalent hexadecimal now. So what is that, this group? 1110, which is nothing but what? Which is equivalent to, in hexadecimal, E. And here it is 1101, which is equivalent to D. 0001, which is equivalent to 1. Similar way, here also 0111, which is nothing but what? Which is equivalent to 7. And what's the remaining? 0100, which is equivalent to 4. So we converted this binary into equivalent hexadecimal. So the final answer is 1DE.74 with base 16. So which means the given octal number 736.35 is converted into equivalent hexadecimal. So that hexadecimal number is 1DE.74 with 16. We can just convert hexadecimal to octal. Okay. Here also it consists of 2 steps. So for the first, for the given hexadecimal number, that can be converted into its equivalent binary, and then that binary number that can be finally converted into octal. Okay. So here also, for example, I am considering A4C.6 with the base 16, which means the given number is hexadecimal. But what's the question is, we have to convert this hexadecimal into equivalent octal. So first we are going to write that is a 4-bit binary equivalent for each digit of hexadecimal. And then we can just convert that into octal. So for example, A4C.6. So we are going to write this hexadecimal to binary representation. So from hexadecimal to binary means we have to represent in terms of 4 bits. So C is nothing but 1100, 4 is nothing but 0, 1, 0, 0. A is nothing but 1, 0, 1, 0. Similar way, 6 is equivalent to 0, 1, 1, 0. So we have converted this given hexadecimal into binary. Now what we are going to do is, we are going to convert this binary into the equivalent octal. So in that case, what you have to do is, we know how to convert from binary to octal. What you have to do? So you have to start from the LSB bit. So we can just group 3 bits as a group. So that is 0, 0, 1 as a group, and then this 1 and this 0, 0 as a group, and then 1, 0, 0 as a group, finally 1, 0, 1 as a group. That is, for example, like this. So what is this? So 1, 0, 0, 1, that is 1, 0, 0 is nothing but which is equivalent to 4. Here it is 0, 0, 1. So this 3 bits as a group, so which is equivalent to 1. Similarly 0, 0, 1 which is equivalent to 1. So what is the remaining? 3 bits are remaining. What are they? 1, 0, 1 which is equivalent to 5. Similar way in the right hand side, here also that is that fractional part. First 3 bits 0, 1, 1. So 0, 1, 1 is equivalent to 3. What's the remaining is 0. Only 1 bit is there. So that we can just add 2 more zeros at the that is most significant end. So which means 0, 0, 0 which is equivalent to 0. So we can write it as 5114.30 with the base 8. So for the given hexadecimal number, the equivalent octal number is this one. So likewise, we can convert this hexadecimal into. So now we are going to consider any base 2 decimal. So the base may be any number that can be converted into equivalent decimal number. Okay, so that can be done by multiplying each digit by its weight and then finally summing that values. Say for example, binary to decimal. So I'll repeat, converting from any base to decimal that can be done by multiplying each digit by its weight, at the same time finally summing all the values. Okay, so for example, we are going to consider binary to decimal. So say for example, this is a given binary number with integer as well as fractional value. So for the integer value, we have to represent that weights in terms of 2 power 0, 1, 2, 3 like that. Suppose if it is in fractional, in that case we have to represent that weights in terms of 2 power minus 1, 2 power minus 2 and so on. So for example, 1, 0, 1, 0, 0.01 with base 2. So this is the given binary. So the question is, we have to convert this binary into decimal. So what do you have to do? So again we have to start from the LSB bit. I told you how to represent that weights for the all the numbering systems, isn't it? So here we can start from the least significant bit for the integer value. So this is the least significant bit 0. So we can start from here. So 0 into 2 power 0, 1 into 2 power 1, 0 into 2 power 2, 1 into 2 power 3. So here we are writing the same. 0 into 2 power 0 plus 1 into 2 power 1 plus 0 into 2 power 3 plus 1 into 2 power 3. So this is for the integer alone. Point for the fractional value. Again we have to start from in this direction. So 0 into 2 power minus 1 plus 1 into 2 power minus 2. So we can just write the equivalent values. 1 into 2 power 3 is 8. 0 into 2 power 2 is 0. 1 into 2 power 1 is 2. 0 into 2 power 0 is 0. Point. 0 into 2 power minus 1 is 0. 1 into 2 power minus 2. So 2 power minus 2 is nothing but it's nothing but 1 by 4. So 1 by 4 is 0.25. So we can just add all these values together. So 8 plus 2 it's 10. So the fractional value is 0.25. So 10.25 with base 10. So likewise we can just convert any base to decimal by giving its weighted value, at last summing all the values together. So this is for example binary to decimal. Example, as I told you, any base. Here it is decimal to, that is binary to decimal. Here it is base is 8, which means octal to decimal. Here base is 16, so which means hexadecimal to decimal. Sometimes the base may be some other number also. Say for example here that base value is 5. So from base 5 to the equivalent decimal values. So always we have to start from the weighting from LSB bit to MSB bit, and for the fractional value in this direction. For the fractional values, you have to give that weight in terms of 2 power minus 1, 2 power minus 2 if it is base 2. Suppose if it is base 5, then we have to write it as 5 power minus 1, 5 power minus 2 and so on. So this is for the example to convert any base value to the decimal. Decimal to any base. So far we discussed is any base value to decimal. Now it is in reverse. That is decimal to any base. So that any base in the sense it may be any number. It may be 5, it may be 7 or it may be 9 and so on. Okay. So while converting this decimal to any base, there are two methods. That is, there are two steps. One is for the integer part, we have to use that successive division method. Suppose if there is a fractional part is there, in that case, we have to use successive multiplication method. Please remember that. So, the decimal number which may consist of integer as well as fractional. It depends. Sometimes it may consist of only that integer. Sometimes which may consist of only fractional part. Sometimes both also. Okay. So, in that case, if it is an integer, for the integer part, we have to use that method called successive division method. And for the fractional part, we have to use that successive multiplication method. Okay. The procedure that has to be followed while doing that integer and for the fractional part. So I'll just explain that steps by doing this conversion. So I'm considering decimal to binary. So the given decimal number is 125 with base 10. So conversion from decimal to base 2, which means binary. So what is it? 125 is nothing but, as we know that it's an integer number, so that we can use that successive division method. So successive division by, what is the question is? We have to convert that final value as binary, no? So that successive division by 2. Suppose if the conversion is from decimal to octal, then successive division by 8. Is it clear? So it is, since the final value should be in terms of binary, so we have to use that successive division by 2. So the given number is 125, so we are dividing by 2, so it is 62, so remaining is 1. Again by 2, so it is 31, the remaining is 0. And again by 2, it's 15, so remaining will be 1. And then 15 by 2, it's 7 times, the remaining will be 1. Similar way like this. At last, we have to consider this binary only in this direction, that is from left to right. Okay. So since the first digit is 0, so that we can just ignore it. There is no meaning of that 0 in left hand side. Listen, it most significant bit. So we can start writing from here. So 1, 1, 1, 5 ones, 0, 1. So finally we can just write it binary equivalent in this way. I am considering the one. Okay. 108. Again, it's an integer. Since the conversion is from decimal to binary, so obviously we have to use successive division by 2. So 108 by 2. So finally we'll be getting that binary value like this. So as I told you, we have to consider in this direction. So 1, 1, 0, 1, 1, 0, 0. So this will be the final binary equivalent. So similar way, decimal to octal conversion. So here I am considering both integer as well as fractional value. So as I told you, for the integer we have to use that successive division method, and for the fractional value we have to use that successive multiplication method. Since the conversion is from decimal to octal number, so successive division by 8, here it is successive multiplication by 8. Okay. 2477. Since it is an integer, so successive division by 8. Why? Because the conversion is from decimal to octal, so it is divided by 8. So we'll be getting that remaining value as 4, 6, 5, 5. So always you have to consider in this direction. And similar way for the fractional value is 0.64. So 0.648, 0.64 into 8. So we'll be getting it as 5.12. So here always you have to consider only that integer values. Again, this fractional value that has to be multiplied with 8 again. So 0.12 into 8 will be getting it as 0.96. So again this 0.96 that has to be multiplied with 8. Again we'll be getting it as 7.68. And again this 0.68 into 8, 5.44 and so on. So in this case, for the fractional, we have to consider that values, only that integer values, but in this direction, that is 5, 0, 7, 5. Only for the integer, we have to consider from left to right. And for the fractional values, we have to consider that integer value alone. And at the same time, we have to consider that value only from top to bottom. Please remember. So what's the final? So 4, 6, 5, 5 point. So this value is 5075 with the base 8. So likewise, we can just convert decimal to octal. So next one is decimal to hexadecimal. So as I told you, again it's an integer. So we can just use that repeated division by 16. Why? Because the conversion is from decimal to hexadecimal. So how will you write this one? 9, 10, 15. So what's the conversion is? Hexadecimal, no? So 9. What is the 10 equivalent in case of hexadecimal? A. 15 means F. So we can write it as 9 A F with base 16. So likewise, we can just convert hexadecimal. Now next one is ones complement. So ones complement of any binary number is the number that results when we change all ones to zeros and zeros to ones. So just changing all zeros to ones and ones to zeros. That's nothing but ones complement. So which means that which performs the NOT operation. That is inverter operation. So 1 1 0 1 0 0 1 0. For example, this is a given binary. The condition is that here we are going to take ones complement. So as I told you, we can just change it zeros to ones and ones to zeros. So 1 means 0, 1 means 0, 0 means 1. So which performs NOT operation, which is nothing but ones complement. One is 2's complement. So what is 2's complement is, for the given binary number, first you have to write that 1's complement, and then by adding 1 to the LSB bit. So that gives you the 2's complement value. So say for example 35 in 8-bit 2's complement form. Question is express 35 in 8-bit 2's complement form. So we can write that 35 is nothing but decimal number. We can just write the equivalent binary number first. So the equivalent binary number for the given 35, the number 35 is 0010011. Now say for example this is the given binary. So what's the question is, we have to find the 2's complement. As I told you what you have to do, first you have to take the 1's complement first. 1's complement is nothing but changing zeros to ones and ones to zeros. So this is nothing but 1's complement. And with that 1's complement number, we have to add 1 to the LSB bit. So 0 plus 1, it's nothing but 1. So 0 as it is, 1 as it is, and this 1 as it is, 0, 1, 1 as it is. So this is the final 2's complement for the given number 35. So likewise, we can convert the 2's complement. So these are the some examples. You can, if you want, you can just work out these problems, and side by side, we can just you can just verify the answers also. Okay, thank you.